February 23, 1945, Elsdorf, Germany. The massive tank sat burning in the village square, its turret blown completely off the hull. German recovery crews from Panzer Brigade 106 approached cautiously, examining what remained of this new American vehicle they had destroyed just hours earlier. The designation stenciled on the shattered hull read M26. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Wehrmacht technical officers had received fragmentary intelligence reports about a new American heavy tank arriving in Europe, but seeing the physical wreckage made those reports real in ways that classified documents never could. This tank represented the final evolution of American armored doctrine, arriving too late to change the war's outcome, but early enough to reveal truths about German tank development that would haunt their engineers for decades. The Pershing bore serial number USA 3081970, built by Fisher Tank Arsenal in Grand Blanc, Michigan. It belonged to the 3rd Armored Division, part of the first shipment of these new tanks to reach European combat zones. Personnel from the German Recovery Unit photographed every accessible component before American forces could reclaim the position. Every measurement contradicted assumptions German engineers had maintained about American capabilities since 1942. The armor was thicker than any previous Sherman variant. The gun was substantially more powerful than the 75mm weapon Germans had grown accustomed to engaging. The entire design philosophy suggested that American industry had solved problems German engineers believed would require years of development. The wreckage told a story that went far beyond this single destroyed vehicle. At Wehrmacht headquarters in Berlin, intelligence analysts compiled reports about American tank development that painted a disturbing picture of industrial capability. The Americans had designed, tested, and deployed an entirely new heavy tank in less time than Germany required to address chronic reliability problems in existing designs. This wasn't the cautious, methodical American approach that German planners had expected. This was rapid development, backed by manufacturing capacity that could turn prototypes into combat-ready vehicles within months. As German forces retreated across the Rhine, technical intelligence units prepared assessments that would reveal uncomfortable truths about comparative engineering philosophies. The Pershing represented American heavy armor, but more importantly, it demonstrated that American industry could iterate, improve, and deploy new designs while simultaneously producing existing vehicles in overwhelming quantities. German tank development programs, by contrast, had become trapped in a cycle of complexity that consumed resources without delivering proportional battlefield advantage. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Spring 1945 brought chaos to Germany as Allied forces closed from all directions. In this desperate final phase, German technical intelligence worked frantically to document American equipment capabilities, knowing that whatever lessons could be learned would arrive too late to influence the current conflict. But the engineers gathering data understood they were creating a record that would matter for whatever came after defeat. The M26 Pershing had begun development years earlier, as American planners recognized the Sherman's limitations against German heavy armor. Initial design work started in 1942, when reports from North Africa indicated that German tanks possessed superior firepower and armor protection compared to American vehicles. The Ordnance Department initiated development of what would eventually become the T-26 heavy tank, predecessor to the production M26. American tank development followed a methodical process that prioritized reliability and manufacturability over rushing vehicles into production. Engineers at Aberdeen Proving Ground tested multiple prototypes, evaluating automotive performance, armor protection, and weapon effectiveness. The development timeline stretched across 3 years, not from technical incompetence but from deliberate testing that ensured the final vehicle would function correctly under combat conditions. This approach reflected lessons American industry had learned through Sherman production. Build vehicles that work reliably, rather than rushing sophisticated designs into service before resolving fundamental problems. The extended development period for the Pershing, allowed engineers to incorporate improvements based on combat feedback from Sherman operations in North Africa, Italy, and France. German intelligence received its first concrete information about the new American tank in late 1944. Reports from agents in the United States described a vehicle significantly heavier than the Sherman, mounting a 90mm gun derived from anti-aircraft weapons. The information seemed plausible given American industrial capacity, but German analysts struggled to understand why Americans would develop heavy armor when their existing Sherman production already overwhelmed German manufacturing. The strategic logic became clearer when examined through American planning documents captured later. American commanders recognized that Sherman tanks, while mechanically reliable and produced in vast quantities, struggled against German Panthers and Tigers in direct combat. The 75mm gun that had been adequate in 1942 proved insufficient against the frontal armor of German heavy tanks encountered in 1944. American doctrine emphasized combined arms operations where Shermans worked alongside tank destroyers, artillery, and air support to overcome German armor advantages. This approach succeeded tactically but imposed casualties that American commanders found unacceptable when a technical solution seemed achievable. The Pershing program accelerated in late 1944 as planners anticipated continued fighting into 1946 if Germany refused surrender. Production authorization came in November 1944. Fisher Tank Arsenal, which had been producing M4A3 Sherman variants, received contracts for the new vehicle. The first production, Pershing, rolled off the assembly line in January 1945. Within weeks, the first 20 vehicles were being loaded onto ships bound for Europe. The timeline from production authorization to combat deployment measured just 3 months, demonstrating manufacturing agility that German industry could not match under wartime conditions. The Pershing weighed 41.7 tons, substantially heavier than the 33-ton M4A3 Sherman, but lighter than the 56-ton German Tiger II. This weight represented deliberate compromise. American engineers wanted armor sufficient to resist German 88mm guns at combat ranges, while maintaining automotive reliability and strategic mobility. The vehicle had to be transportable by existing Allied landing craft, transportable across the temporary bridges Allied engineers constructed, and operable using American logistics that emphasized mobility over static defense. The armor protection reflected this balanced approach. Frontal hull armor measured 4 inches at 46 degrees from vertical, providing effective thickness of approximately 5.8 inches against direct fire. Turret front armor measured 4 inches at vertical, with gun mantlet armor reaching 6 inches in critical areas. Side armor measured 3 inches, adequate against most German anti-tank weapons at typical combat ranges, but vulnerable to 88mm guns and larger calibers. German technical officers examining destroyed Pershings in March and April 1945 documented armor thickness with precision instruments, comparing measurements against their own vehicles. The protection levels matched or slightly exceeded Panther specifications while remaining substantially less than Tiger II armor. What impressed German analysts was not absolute armor thickness, but the quality of armor plate manufacturing and the efficient arrangement that provided protection without excessive weight. American armor plate demonstrated consistently high quality across all examined samples. No significant variations in hardness, no manufacturing defects that created weak points, no evidence of the quality degradation that plagued German armor production in late 1944 and early 1945, as strategic bombing disrupted supply chains and forced substitution of inferior materials. Every plate examined showed professional heat treatment and proper alloy composition. The Americans had maintained manufacturing standards even while producing armor in quantities that exceeded total German output. The 90mm M3 gun, mounted in the Pershing turret, provided firepower equivalent to German 88mm weapons. Muzzle velocity reached 2,800 feet per second with armor-piercing ammunition, sufficient to penetrate Panther frontal armor at 1,000 yards and Tiger I frontal armor at closer ranges. The gun derived from the 90mm anti-aircraft weapon already in mass production, allowing American industry to leverage existing manufacturing capacity rather than developing entirely new production facilities. This practical approach to weapon selection demonstrated American engineering philosophy. Rather than pursuing theoretical maximum performance through custom weapon development, American designers adapted existing weapons that could be manufactured quickly using available industrial capacity. The 90mm gun was not optimal for tank use in all respects, but it was adequate for defeating German armor while being immediately available in quantity. The fire control system impressed German technical officers who examined captured Pershings intact enough for assessment. The turret incorporated a gyroscopic stabilizer for the main gun, allowing the gunner to keep the weapon aimed at the target even while the vehicle moved across rough terrain. German tanks lacked this capability, requiring crews to stop before firing accurately except at very close ranges. German engineers had experimented with gun stabilization in the 1930s, but abandoned the effort due to technical complexity and manufacturing difficulties. American engineers solved the problem through systematic development and incorporated the technology as standard equipment across Sherman and Pershing production. The advantage in combat proved significant, allowing American tanks to fire accurately while maneuvering, a capability German crews could only achieve by stopping their vehicles and presenting static targets. The automotive components of the Pershing reflected American priorities regarding reliability and ease of maintenance. The Ford GAF V8 engine produced 500 horsepower at 2,600 RPM, providing adequate power for the vehicle's weight. The engine derived from the Ford GAA used in late production Sherman tanks, representing evolutionary improvement rather than revolutionary redesign. American engineers had taken a proven engine, increased displacement slightly, and adapted it for the heavier vehicle. This conservative approach to powertrain design ensured that mechanics familiar with Sherman maintenance could service Pershing engines using similar procedures and tools. The transmission used torquematic automatic shifting, a sophisticated system that eliminated the need for manual gear changes during operation. German technical officers examining this transmission expressed amazement at the complexity Americans had successfully mass-produced and integrated into combat vehicles. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. German tanks used manual transmissions, requiring skilled drivers to operate effectively. The Panther transmission, in particular, demanded careful technique to avoid damage, with explicit restrictions against certain gear combinations and turning movements that would destroy components. American automatic transmissions made their tanks operable by drivers with minimal training, reflecting the industrial democracy philosophy that any competent soldier should be able to operate military equipment without extensive specialized education. The suspension system used torsion bars, a design feature German engineers had pioneered and considered superior to other suspension types. Seeing Americans adopt torsion bar suspension validated German technical assessments, while simultaneously demonstrating that American industry could manufacture these components in quantity without the quality problems that plagued German production. Each examined Pershing had suspension components showing excellent manufacturing quality, with no signs of the stress fractures or material defects common in late-war German vehicles. By March 1945, approximately 40 Pershings had reached European combat zones. The vehicles saw limited action due to their late arrival and the fluid tactical situation as German forces collapsed across all fronts. Several notable engagements occurred where Pershings engaged German armor under conditions that allowed tactical assessment. The most documented engagement occurred at Elsdorf on February 26, 1945, when Pershing No. 33 from the 3rd Armored Division engaged a German Tiger I at approximately 900 yards range. The Pershing's 90mm gun penetrated the Tiger's frontal armor with 3 hits, destroying the vehicle. This engagement, photographed and documented by American combat cameramen, provided clear evidence that American heavy tanks could defeat German armor in direct combat. German tank crews who survived encounters with Pershings reported the experience in after-action assessments. The reports consistently noted the Pershing's ability to fire accurately while moving, a capability that gave American tanks significant tactical advantage. German crews were accustomed to fighting Shermans, whose 75mm guns required multiple hits to defeat heavy German armor. The Pershing's 90mm gun could penetrate German tanks with single hits at ranges where German weapons were equally effective. More troubling from the German perspective was what the Pershing represented about American industrial trajectory. German intelligence officers examining combat reports recognized that this new tank demonstrated American capacity for rapid development and deployment. The vehicle had gone from initial production to combat operations in Europe within 2 months, a timeline that would have been impossible for German industry even before strategic bombing disrupted manufacturing. The few Pershing wrecks that German forces captured intact enough for detailed examination underwent hurried technical assessment in field conditions. Wehrmacht recovery units photographed components, measured dimensions, and attempted to understand design choices before American counterattacks forced withdrawal. The assessments, conducted under combat conditions without access to proper facilities or instruments, nevertheless provided valuable intelligence about American capabilities. One technical report from a Panzer brigade engineer officer documented examination of a Pershing destroyed near Cologne in early March 1945. The officer noted the internal arrangement of the vehicle, remarking on generous crew space that exceeded German tank designs. American tankers operated in relatively comfortable conditions, with adequate room for ammunition storage, fire control equipment, and crew positions that did not force personnel into cramped quarters. German tanks, designed to minimize external dimensions and maximize armor protection, sacrificed crew comfort for combat effectiveness. Panther and Tiger crews operated in confined spaces where loaders struggled to handle ammunition and commanders had limited visibility. American designers had prioritized crew effectiveness, understanding that comfortable crews fought more effectively over sustained periods than exhausted personnel crammed into minimal space. The examination report noted the electrical system, which included multiple generators and backup power supplies, ensuring that critical systems remained operational even if the main engine failed. German tanks typically had single generators with no backup capability, meaning engine failure eliminated turret power traverse and other electrical functions. American redundancy seemed like wasteful over-engineering to German eyes, but it reflected design philosophy that prioritized keeping vehicles functional under damage conditions. Another assessment examined the tracks and running gear of a Pershing abandoned during the Rhine crossing operations. The track design used center guides engaging with guide teeth on the drive sprocket, a system that prevented track throwing even under severe side loads during turns. German tanks used various track retention systems, but none as inherently stable as the American center guide approach. The running gear showed evidence of robust construction with wear patterns suggesting the suspension could handle extended operations without frequent maintenance. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By April 1945, German technical intelligence had accumulated sufficient information about the Pershing to produce comprehensive internal assessments. These documents, intended for senior Wehrmacht officers and armaments ministry officials who still functioned amid Germany's collapse, painted a sobering picture of comparative capabilities in late-war tank development. The assessments acknowledged that the Pershing represented a significant improvement in American armored capability, providing firepower and protection that matched or exceeded most German tanks while maintaining the automotive reliability that had characterized all American armored vehicles. More significantly, the reports noted that American industry had developed and fielded this new tank while simultaneously maintaining Sherman production at rates exceeding all German tank output combined. This dual capability, producing both existing and new designs without disrupting either program, demonstrated industrial depth that Germany had never possessed. German tank production required complete factory retooling when transitioning between models. Panther production necessitated shutting down Panzer IV lines. Tiger II production displaced Tiger I manufacturing. American industry produced both Sherman and Pershing variants simultaneously from different facilities, showing production flexibility that German planners had considered theoretically possible but practically unachievable. The technical assessments also examined what the Pershing revealed about American development timelines and iteration speed. German intelligence estimated approximately 3 years from initial T-26 prototype to combat-ready M26 production vehicle. This timeline included extensive testing, multiple prototype iterations, and systematic resolution of technical problems before authorizing mass production. German tank development followed similar timelines, but with critical differences in execution and results. The Panther tank, rushed into production for Operation Citadel in July 1943, had required more than a year of subsequent modification to achieve acceptable reliability. Early Panthers suffered catastrophic mechanical failures that eliminated more vehicles than enemy action during initial combat deployment. The Americans had taken longer to develop the Pershing, but when production began, the vehicles worked correctly without requiring extensive field modification programs. This difference reflected fundamentally different approaches to development and production. German development emphasized rapid fielding of technically advanced vehicles, accepting that reliability problems would be resolved through field experience and subsequent modification. American development emphasized thorough testing before production authorization, ensuring vehicles functioned correctly from initial deployment. In total war conditions, the American approach proved more effective despite appearing slower in development phase. German engineers examining Pershing components recognized design choices that reflected mature industrial thinking. The engine used common automotive components wherever possible, allowing manufacturers to leverage existing supply chains rather than creating entirely new production systems. The transmission, despite its sophisticated automatic operation, used internal components similar to those in commercial heavy equipment. The electrical system employed standard commercial electrical parts rated for military environmental conditions. These design choices minimized production bottlenecks and simplified logistics. American quartermasters could source Pershing spare parts from multiple manufacturers using specifications that ensured interchangeability. German logistics, by contrast, struggled with unique components, requiring specific manufacturers and custom production processes that could not be easily substituted when bombing disrupted facilities. The few German tank crews who encountered Pershings in combat and survived to report their experiences provided tactical assessments that complemented technical intelligence. The reports consistently emphasized the Pershing's effectiveness in direct engagement, noting that American heavy tanks no longer required numerical superiority or tactical advantage to defeat German armor. The 90mm gun proved effective against Panther frontal armor at typical combat ranges, eliminating the protection advantage German crews had relied upon when fighting Shermans. More concerning was the psychological impact of facing American tanks that matched German vehicles in protection and firepower while maintaining the reliability advantages that characterized all American equipment. German tank crews had grown accustomed to mechanical failures that eliminated vehicles before they reached combat. Pershing crews apparently experienced the same automotive reliability that Sherman crews had enjoyed, meaning American heavy tanks could be counted on to function when needed. One Panther Company commander who engaged Pershings near Paderborn in early April 1945 submitted a report noting that American tank crews operated with confidence, suggesting their vehicles would perform as expected. German crews, by contrast, constantly worried about mechanical failures that might immobilize their tanks at critical moments. This psychological burden, accumulated over years of operating unreliable vehicles, affected combat effectiveness in ways that technical specifications never captured. The commander's report concluded with an observation that American tank development had followed a logical progression from adequate to superior. The Sherman had provided reliable mobility and adequate firepower for combined arms operations. The Pershing added heavy armor and powerful armament while maintaining the automotive excellence that made American tanks operationally dependable. German tank development had pursued sophistication that proved difficult to manufacture and maintain, resulting in vehicles that were impressive in specifications but unreliable in sustained operations. By late April 1945, organized German resistance was collapsing across all fronts. Technical intelligence officers evacuated westward, carrying documents and assessments that represented years of systematic analysis of enemy equipment. Among these documents were reports on the M26 Pershing that acknowledged what German engineers had been reluctant to admit since examining captured Shermans in 1943. American tank development had surpassed German capabilities not through superior theoretical knowledge, but through industrial maturity and design philosophy that prioritized practical effectiveness over impressive specifications. The Pershing represented the culmination of this approach, a vehicle that combined adequate protection, effective firepower, and reliable automotive performance in a package that American industry could manufacture and American logistics could support in sustained combat operations. The examination of destroyed and captured Pershings continued through the final weeks of the war, as German technical intelligence units raced against time and collapsing front lines. Engineers documented what they could access, knowing that systematic testing facilities like Kummersdorf were either destroyed or already in Soviet hands. The assessments conducted under desperate field conditions nevertheless revealed patterns that confirmed what German engineers had gradually learned through years of examining American equipment. The Pershing's final drives demonstrated the same engineering philosophy that had made Sherman tanks so reliable. German engineers examining these components found robust construction with substantial design margins that exceeded immediate requirements. The gearing used herringbone-cut teeth that distributed stress across multiple contact points simultaneously, a manufacturing technique that American industry had mastered decades earlier, but German tank production had never successfully implemented at scale. German final drives, particularly those in Panther tanks, had proven chronically unreliable throughout the war. The straight-cut gears required precise tolerances and careful heat treatment to function properly. Manufacturing quality degraded as strategic bombing disrupted supply chains and forced substitution of inferior materials. By early 1945, Panther final drives were failing catastrophically at rates that made operational planning nearly impossible. Some units reported that 30% of their tanks were immobilized by final drive failures before even reaching combat zones. The Pershing final drives examined by German engineers showed no such vulnerabilities. The components were overbuilt relative to calculated stress requirements, providing durability that would allow extended operations without maintenance intervention. American engineers had designed for abuse, understanding that combat vehicles would operate under conditions that exceeded peacetime engineering assumptions. German engineers had designed to calculated specifications, assuming proper maintenance and operating procedures that proved impossible to maintain under wartime conditions. One technical assessment from a Wehrmacht engineering officer examined the Pershing's transmission in detail after German forces captured an intact vehicle abandoned when its crew evacuated during an American advance near Kassel in late March 1945. The officer spent several hours documenting the Torquematic automatic transmission before American counterattacks forced withdrawal. His report expressed professional admiration for the engineering sophistication Americans had successfully mass-produced. The transmission used a torque converter that multiplied engine power during acceleration, providing smooth power delivery without the shock loads that damaged German manual transmissions when drivers made shifting errors. The automatic shifting eliminated the need for skilled double-clutching techniques that German drivers required years to master. The entire system reflected a design philosophy that assumed operators would be minimally trained conscripts rather than professional mechanics. Yet the transmission needed to function reliably under combat stress. German transmissions, even when operated by highly trained drivers following proper procedures, suffered frequent failures. The Panther transmission was so fragile that field manuals explicitly warned against using third gear, except when absolutely necessary, because that gear ratio failed with such regularity. Drivers learned to shift from second directly to fourth gear to avoid destroying the transmission. Such restrictions severely limited tactical flexibility and required constant attention to mechanical preservation rather than combat effectiveness. The Pershing transmission, by contrast, required no such operator caution. American tankers could shift freely through all gears without concern for damaging components. The automatic operation meant that drivers could focus on vehicle positioning and tactical awareness rather than managing complex mechanical systems. This difference, multiplied across thousands of vehicles and millions of operational hours, represented a significant advantage in combat effectiveness that technical specifications alone could never reveal. The cooling system of the Pershing demonstrated another area where American automotive engineering exceeded German capabilities. The radiator and cooling fan were sized generously, providing cooling capacity that exceeded requirements under normal operating conditions but proved essential during sustained combat operations when engines ran at high power output for extended periods. German tanks, designed with minimal cooling capacity to reduce weight and complexity, frequently overheated during sustained operations in warm climates or when operating at maximum power output. The air filtration system on the Pershing used cyclonic separation, followed by oil bath filtering, a robust design that handled dust and debris without the frequent clogging that plagued German air filters. Tank operations inevitably produced enormous dust clouds that choked air filters within hours of combat operations. German tanks required frequent filter cleaning and maintenance to prevent engine damage from ingested debris. American systems functioned for extended periods without maintenance intervention, keeping vehicles operational when German tanks were being serviced. These seemingly minor differences in cooling and filtration systems accumulated into significant operational advantages. American tanks could sustain combat operations for days without mechanical maintenance stops. German tanks required daily maintenance even when not engaged in combat, consuming scarce mechanic labor and keeping vehicles out of action during critical periods. The reliability difference determined which force could maintain offensive momentum and which had to carefully ration limited operational vehicle availability. By May 1945, the war in Europe ended with Germany's unconditional surrender. The technical intelligence assessments of American equipment, including comprehensive documentation of the Pershing tank, became part of the historical record that shaped post-war understanding of why Germany had lost the industrial and technological competition that underpinned military capability. The Pershing itself saw limited service during World War II. Only approximately 200 vehicles reached Europe before Germany surrendered, and fewer than 20 engaged in actual combat operations. The vehicle's impact on the war's outcome was negligible, given its late arrival, but the Pershing's significance extended far beyond its minimal combat record. The vehicle represented validation of American tank development philosophy and confirmation that American industry could produce sophisticated heavy armor while maintaining the reliability and manufacturability that characterized all American military equipment. German engineers examining Pershing tanks in April and May 1945 recognized that American tank development had reached maturity. The progression from M3 Grant through multiple Sherman variants to the Pershing demonstrated systematic improvement based on combat experience and rigorous testing. Each iteration incorporated lessons from previous designs while maintaining automotive reliability that German tanks never achieved. The Americans had proven that heavy armor, powerful armament, and mechanical dependability were not mutually exclusive design goals when supported by mature industrial capability. The contrast with German tank development could not have been more stark. German tanks had become progressively more sophisticated and less reliable as the war continued. The Panzer IV, which had been adequately reliable in 1941, gave way to the Panther, which suffered chronic mechanical failures through 1943 and into 1944. The Tiger, impressive in specifications, required constant maintenance and frequent repairs. The Tiger II, theoretically the most powerful tank of the war, proved so unreliable that many were abandoned due to mechanical failure rather than combat damage. German engineers understood the technical reasons for these reliability problems. Insufficient testing before production authorization meant that design flaws appeared only after vehicles entered service. Manufacturing quality degraded as strategic bombing disrupted supply chains, and forced use of inferior substitute materials. Skilled labor shortages led to increasing use of slave labor that introduced deliberate sabotage. The accumulation of these factors created a death spiral where vehicles became less reliable even as tactical situations demanded greater operational availability. American tank development avoided this spiral through systematic testing, quality manufacturing, and design choices that prioritized reliability. The extended development period for the Pershing, which German planners had initially interpreted as American industrial slowness, actually represented thorough engineering that ensured the vehicle worked correctly from initial deployment. American industry maintained consistent manufacturing quality, despite producing vehicles in quantities that exceeded German output by factors of 5 to 10. American designers specified components with generous margins that tolerated manufacturing variations and operator abuse without catastrophic failure. The post-war fate of the Pershing illustrated American pragmatism regarding military equipment. The vehicle served as the United States Army's primary heavy tank through the immediate post-war period and into the Korean War, where it provided crucial armor support during desperate defensive operations in 1950. The tank proved effective against North Korean T-34-85 tanks, validating the 90mm gun's capability against Soviet-designed armor. However, American planners recognized that the Pershing represented a transitional design rather than an optimal solution for future armored warfare. Development began immediately on improved vehicles that would become the M26 Patton, M47, and M48 series. These tanks incorporated lessons from Pershing combat experience while addressing limitations in automotive performance and firepower. The progression demonstrated American willingness to acknowledge imperfection and continuously improve rather than defending existing designs as adequate. German engineers who survived the war and entered the post-war period carried with them lessons learned through years of examining American equipment. Many found employment with the occupying powers, working in technical positions that leveraged their expertise. Some emigrated to the United States, contributing to American defense programs during the Cold War. Others remained in Germany, participating in reconstruction efforts that rebuilt the nation's industrial base. These engineers brought with them understanding that German pre-war confidence in technical superiority had been fundamentally misplaced. Germany had possessed excellent theoretical knowledge and scientific expertise, but lacked the industrial maturity and manufacturing philosophy necessary to translate that knowledge into reliable military equipment producible at scales modern warfare demanded. American industry, built on decades of commercial automotive experience and mass production expertise, had proven decisively superior when challenged by total war conditions. The lessons influenced German tank development when West Germany began rearmament in the 1950s. The Bundeswehr's first main battle tank, the Leopard 1, incorporated design philosophy that owed more to American thinking than traditional German approaches. The vehicle emphasized reliability and maintainability over maximum firepower and armor protection. It used proven automotive components rather than custom-designed systems. It incorporated substantial design margins that provided growth potential for future upgrades. The Leopard 1 became one of the most successful tank designs of the Cold War era, serving with numerous armies and remaining in production for decades. The contrast between Leopard 1 development and late-war German tank programs illustrated how thoroughly German engineers had absorbed lessons from defeat. Where Panther and Tiger development had prioritized impressive specifications, achieved through complex engineering, regardless of manufacturing difficulty, Leopard 1 development emphasized practical effectiveness through sound engineering that could be manufactured reliably and maintained in field conditions. The shift in philosophy reflected direct learning from examination of American vehicles like the Sherman and Pershing that had proven so effective during World War II. German engineers who had examined captured American tanks during the war later acknowledged in memoirs and interviews that those examinations had been educational experiences that challenged their assumptions. One former Wehrmacht technical officer who worked on Leopard 1 development stated in an interview conducted in the 1970s that examining the Pershing in April 1945 had been humbling. He had expected to find crude American engineering that achieved results through brute force and excess material. Instead, he found sophisticated solutions to complex problems, executed with manufacturing quality that exceeded late-war German standards. The officer recalled measuring the armor plate thickness on a destroyed Pershing and being impressed by the consistent quality across all examined sections. German armor plate in early 1945 showed significant quality variation depending on when and where it had been manufactured. Strategic bombing had disrupted supply chains for alloying materials, forcing substitutions that degraded armor quality. Labor shortages meant that inexperienced workers and slave laborers performed heat treatment operations that required skill and experience to execute properly. American armor plate showed none of these quality problems. Every section examined met specifications. The heat treatment was uniform. The alloy composition was consistent. The Americans had maintained manufacturing standards even while producing armor in quantities that far exceeded German output. This achievement demonstrated industrial depth that Germany could never match even before strategic bombing intensified. Another German engineer who examined Pershing automotive components in May 1945 later worked as a consultant for American defense contractors during the Cold War. In his unpublished memoir, he described his reaction to examining the Pershing's Ford GAF engine. He had expected to find a crude power plant that achieved adequate performance through excessive displacement and low specific output. Instead, he found a well-engineered V8 that demonstrated mature understanding of automotive design principles. The engine used overhead valves that provided excellent breathing characteristics for high power output. The cooling system was generously sized but elegantly designed to minimize weight and complexity. The oil system incorporated a full-flow filter that protected internal components from wear, a feature that German tank engines lacked despite being theoretically superior in specific power output. The entire engine reflected decades of commercial automotive experience applied to military requirements. The engineer noted that German tank engines were designed by specialists who understood theoretical thermodynamics and mechanical engineering, but lacked practical experience with high-volume manufacturing and field maintenance. American tank engines were designed by automotive engineers who had spent careers building power plants that needed to function reliably in customer hands with minimal specialized maintenance. The difference in design philosophy was immediately apparent to anyone who examined both approaches objectively. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out, and don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.